Welcome to The Explainer. Today, we're going to crack open the black box that powers everything from hyper-realistic gaming to the entire AI revolution, the GPU. We're going to build a really simple but powerful mental model for how these incredible chips actually get their work done.
So let's just kick things off with a pretty basic question. How is it that one little chip can be so ridiculously good at certain jobs while the main processor in your computer, the CPU, just can't seem to keep up? Well, the secret isn't just about raw power. It's a completely different philosophy of how to work.
You can think of it this way. A CPU is a generalist. It's like a brilliant project manager that's optimized for what we call latency. It's designed to tackle one really complex task at a time and do it incredibly fast. A GPU, though, it's a specialist. It's built for throughput. Its entire goal is to handle thousands, even millions of simpler, parallel tasks all at the exact same time.
To really get our heads around this, let's imagine the GPU as a massive, super organized factory. This analogy is going to be our guide as we explore how work actually gets done inside the chip. Okay, so this slide right here, this lays out our entire factory analogy. And you'll notice two categories. The software concepts are like the project plan, the instructions. The hardware concepts are the actual physical parts of our factory. We're going to walk through this whole hierarchy, from the top-level project all the way down to a single worker and the tools they use.
So, at the very, very top, we have the grid. This is a software idea that represents the entire job that needs to be done. Let's say we're rendering a frame in a video game. The grid is basically the master blueprint for calculating the color of every single pixel on your screen, the whole shebang. Now, the actual work that's defined by that grid, it gets done on the factory floors. In the real world, these are the physical streaming multiprocessors, or SMs, on the GPU chip. You can think of an SM as a totally self-contained workshop. It's got all the tools and managers it needs to get its tasks done.
Each of those factory floors, each SM, hosts one or more teams. In GPU lingo, these teams are called blocks. Now here is a rule that is just fundamental to how GPUs perform. A team is never split across different factory floors. An entire block always runs on a single SM. And we'll see exactly why that's so critical in just a little bit. All right, let's move to a more microscopic view and see how this all builds up. Now we're zooming right in on the factory floor itself to see how the individual workers are organized and what kind of tools they're using. So the smallest units of work are the threads. These are our individual factory workers. A single thread is basically one instance of your program running, and the tool they use to do all their math, that's the CUDA Core, which is the fundamental number crunching part of the chip. Now, trying to manage every single worker one by one would be just crazy inefficient, right? So the hardware cleverly groups 32 threads together into something called a warp. Think of this as a work crew. A foreman, called the warp scheduler, gives the entire crew of 32 the exact same instruction at the exact same time. This whole concept is called SIMPT, or single instruction, multiple threads.
This lockstep model is unbelievably efficient, as long as everyone is doing the same thing. But it brings up a really fascinating question. What happens when your code has a branch? What if some workers in that crew need to do one thing, and the others need to do something completely different?
Just imagine your code looks something like this. It's a simple if-else statement. It tells the first 16 workers in the crew to follow one path, path A, and the last 16 workers to follow a different one, path B.
And this perfectly illustrates a major performance trap called warp divergence. Because the whole crew has to move in lockstep, the hardware handles this by running both paths, one right after the other. So first, the 16 workers on path A do their thing, while the other 16 just sit there, idle. Then the 16 workers on path B do their work, while the first group waits. The result? You've just slashed your efficiency in half. 50% of your crew is doing nothing at any given moment.
So, knowing about these constraints, like warp divergence, how does the GPU's management layer organize all these teams and workers to squeeze every last drop of performance out of the hardware?
Let's circle back to that really important rule we talked about earlier. A team of workers, a block, is always stuck on a single factory floor, or SM. There's a very, very good reason for this, and it all comes down to the speed of communication.
This table tells the whole story. Just look at the access speeds. Data that's stored locally, right there on the factory floor, in what we call shared memory is incredibly fast. We're talking about 23 clock cycles. But if a worker has to go all the way to the main warehouse, what's called global memory, it takes almost 300 cycles. That is a massive slowdown, more than 10 times slower.
And this chart really just drives that point home. The difference in performance is, well, it's dramatic. If your teams had to constantly walk off their factory floor to go fetch tools and materials from the main warehouse, the whole project would just grind to a halt. It would be a huge, unavoidable bottleneck.
So this is why that rule is so important. Keeping a block on a single SM guarantees 3 things. They get access to that lightning-fast local memory, all the workers can coordinate with each other basically instantly, and it just makes the scheduling job for the hardware way, way simpler. It's a design choice that is all about maximizing speed.
Okay, so we've gone deep inside a single GPU. Now let's zoom all the way out. How do we take these individual factories and connect them all together to build the massive supercomputers that train today's biggest AI models? Well, building a modern AI server is kind of like building a city. You've got the CPUs acting as the city planners, managing the operating system and telling everyone what to do. Then you have the GPUs, our factories, providing all the immense parallel processing muscle. And connecting it all is the specialized high-speed transportation infrastructure.
And this transportation network has 2 main tiers. You can think of NVLink as the internal superhighway, connecting all the factories that are within one industrial park. It's for ultra-fast local traffic. Then, to connect that entire park to other parks all across the country, you use a massive external highway, something like InfiniBand. Both are designed for one thing, moving unbelievable amounts of data as fast as humanly possible.
So, let's just quickly recap the mental model we've put together. First, GPUs are specialists, built for parallel throughput. Second, their work is organized in a really clear hierarchy. Third, teams are kept on their own factory floors to get access to that super-fast memory. Fourth, warp divergence is a key performance killer you have to watch out for. And finally, these things scale up to supercomputer size using dedicated internal and external networks. And that really just leaves us with one final thought. We now understand the architecture of these computational monsters, from the individual worker all the way up to the data center scale. With this kind of incredible power at our fingertips, the only real limit is our own imagination. So the question is, what problems are we going to solve next?